All right, we are back. Happy Wednesday. We're wrapping up chapter 16. So, what that means is, homework one is due tonight. So, do those assigned problems from chapter 16 and snap a picture of it and upload that electronic file to Learning Suite by 11:59 tonight. Don't wait until exactly at midnight. Learning Suite can do funny things. So do yourself a favor and get it in as soon as you can. I notice a lot of people already have it in, so that's good. I can tell it's working. Also, quiz one's due tomorrow night. Uh, it's actually 2 pages, the actual quiz itself, and I think problem 3 you have to do a little bit of inspection of a couple things on Chem352. How many people have been to Chem352? Is that working okay? Yeah, most people, a thumbs up there. You only have to show one transition state for each problem. You don't have to analyze both the endo and the exo for both of them. You can expect both of those on Chem352 if you'd like, but the only thing you need on the quiz one is your analysis of what the endo, the favored transition states for those 2 problems. And then the questionnaire on the second page, fill that out. We'd like to know who you are, especially when you took 351 and any concerns you have there. I always like to read through those and get to know you better there. TA Help Room URL is posted on our Learning Suite website in a couple spots. It's actually a spreadsheet. If you click on that, you'll go to a big sheet where you'll see the different days and the times for all the TAs involved in organic chemistry, not just our class, but all the classes. So the TAs, you don't have to use the TAs that are assigned to your recitation section. You can use any of the TAs there. But I think it's Monday through Friday, 8 in the morning till 6 or 7 at night. Yeah. Gannon's on there too. You can find your TA if you'd like to, but you don't need to zoom in on that. And it is a Zoom link. It's only active at that time. So you need to look at the schedule and click on those URLs that's in that sheet there. And then chapter 17, aromaticity. We'll start on Friday, so no rest for the weary there. We'll be going on there. Questions on any of the business stuff here? All right, let's do a little review together here as a class and see how we do here. We've got a couple of 1.2 or 1.4 additions, HCl, HBr here. And then we have a couple of Diels-Alder reactions. So here we just have butadiene, HBr, 1 equivalent, and that's what it implies there, okay? We may not always say 1 equivalent, but if it's just shown as 1 equivalent, that's all we do. Because we could, if we had excess, we could add both alkenes and get a dibromo, but so we're implied 1. And the temperature is kind of the key thing here. So what are we gonna do? We're gonna do the 1,4 addition, right? What do we call that again? The thermodynamic product. And the key there is it's the more substituted alkene product, okay? So I don't think we need to go through the mechanism there. We'll have time to review before test 1, of course. You should review the mechanism to convince yourself should be the 1,4 addition because of the higher temperature and di-substituted alkene instead of mono-substituted alkene, okay? And then we've got HCl at minus 78 here. So what's going to be our product in this case? Yeah, it will be the 1,2 addition product, okay? So we're going to protonate the end here. We don't always redraw the hydrogens, right? And then we'll have a tertiary cation in resonance with a primary cation. And at low temperature, the nucleophile is going to go to the more substituted cation. Okay, that's the bottom line, remember, for the 1,2 addition. Oh, and then we got a synthesis problem. Let's see. What's this tert-butyl OK thing? No, that's not OK. That's potassium T-butoxide, right? The bulky base that always does what type of reaction? Let's try to review that. That's a 351 reaction. SN2. A couple people giving me the victory sign for SN2, I think there. Okay, so what are we going to do? We're going to eliminate HCl here either from this side or from this side. If we eliminate over here, you see we'll get the conjugated diene. And that's why we're talking about that. So that's our intermediate there. We could eliminate over here, but that would be also a disubstitute alkene, but it wouldn't be resonance conjugated. When we eliminate here, we get the resonance of about 6 kcals per mole between the two alkenes that are conjugated. So that's our first thing. And then HCl, oh, it doesn't matter what the temperature is because this is a symmetric allyl cation. You can protonate either side, it's symmetric, and then trap either position of the allyl cation. Sometimes it doesn't matter, 1, 2, or 1, 4. So in this case, what's the product? It'll be this. And make sure you have the allylic chloride, okay? Don't have the non-allylic chloride formed, okay? We protonate here to give the allyl cation, and then trapping on either end gives the same product there, okay? So you okay on those first 3 questions? Some people are nodding. Some people are nodding the other way. That's okay. But this gives you a little heads up to see how to work the problems there. Okay. Then we got Diels-Alder. And remember with Diels-Alder, we've got a couple things to remember here. The stereochemistry of the dienophile is kind of the key thing there. If it's cis, it will go cis in the product, right? And we see that here. If it's trans here on the dienophile, these two esters will end up trans to each other. That's the first thing to remember. And then the other key thing is the endo rule. Okay. And that's only if you have the 2 stereocenters, especially one at the allylic position also. And it's that relative stereochemical relationship between any stereochemistry coming from the dienophile and then on the diene at the allylic position, okay, that we need to worry about. And then today we'll get into the third aspect of the stereochemistry of the Diels-Alder reaction. That's called the Regio selectivity, okay? And that Regio selectivity is something that's important there when you have an unsymmetric diene and an unsymmetric dienophile, and you don't know how they're going to come together. But we'll look at the resonance structures, and hopefully that'll make some sense. But those are the 3 aspects that I think make the Diels-Alder reaction somewhat tricky. Okay, so let's look at it here. So there's our cyclohexene being formed and our aldehyde. Okay. Now here, notice there's no stereocenters at the allylic position, so we don't need to worry about the endo rule. This is a stereocenter, and it will form as a racemic product, DL, okay? Both up and down. You can draw both of them or just recognize that it is a stereocenter. Both are forming, okay? Here now we have to worry about the endo rule because with cyclopentadiene, we'll have a stereocenter at both of these allylic positions. So what are we going to form here? Well, we're going to have our cyclohexene and then our methylene bridge. Let's draw that up. And we'll look at the models to remind us of this. And then on the dienophile, we have stereochemistry. These 2 hydrogens are cis. So they'll end up what to each other in the product? Cis, right? So let's see. And let's see if you've worked enough problem. These 2 hydrogens both up or both down relative to the methylene. Should I draw them up or down? Yeah, I should draw them up, okay? And so that will be the endo thing. We'll look at that in a second. And then if we have osmium tetroxide, we'll form what? The diol right there, okay? And I think you can draw that. So this whole thing here from the Diels-Alder, and then put 2 alcohols here, both up, okay? Because the anhydride's tucked underneath and kind of blocking that bottom face. So this top face, that's a problem, I think, on the homework, okay? Chapter problems. And that's from 351, right? Osmium tetroxide. Then we got MCPBA. What will that form right here? Well, an epoxide. Okay, And that epoxide, little three-membered ether, will be right there on that. Okay, so you can see some complexity of what we can do there. All right, let's do this one. So we've got another bridged bicyclic thing. And now we have an ethylene bridge here. And our cyclohexene is shown right there. And we'll have one of the esters up and the other ester down. Now we can't put both of them endo, okay? Because one is, across. They're across from each other. So if you put one endo, that's fine underneath there, but you see the trans relationship right there. Okay. Maybe let's look at that transition state. Remind ourselves of the endo rule. So we'll have the anhydride tucked underneath here. And there's our Diels-Alder reaction right there. Okay. And then you'll see here's our methylene coming up right there. And there's our two hydrogens that will be cis to each other and cis to the methylene in the bicyclic thing there. Okay. Now let's look at the models again. So here's our diene. Here's our dienophile. And I'll grab those with my hands where the sigma bonds are forming. And then you see the red ball is in the endo position. It's tucked underneath there. So you'd picture another one over here for the anhydride. It's got two things that are tucked underneath there. But that would be the endo. This would be the exo, which is not favored. That has the pi system of the dienophile out away from underneath the diene. So it doesn't benefit from that secondary orbital overlap. That's the basis for the endo rule. So if this is still tricky for you, make some models and engage with this physically. This is probably the trickiest aspect, I think, of the Diels-Alder, this endo thing. So that's why I like to cover it a couple different times in a couple different contexts. Okay. Questions on any of that? All right. Very good. Let's get into this third aspect here, the Regio selectivity. And what's that a consequence of? Let's give you a reaction, some context here. So how about if we have a methoxy butadiene? So there's a methyl ether on our 1,3-butadiene. And the methoxy ether, you see, is at this one position here. Don't worry about the nomenclature of those things. We haven't covered any of that. We'll do some nomenclature later, I think, in the aromatic chapter. But let's react this with dienophile, acrolein, the unsaturated aldehyde. And we can do it in this manner. Push your electrons around there. The mechanism's always easy for the Diels-Alder reaction. But we've got some issues here, right? We've got our old friend stereochemistry at the allylic position, right? At least got to worry about that. The other thing we need to worry about is what? How about if we flip the aldehyde over like that? And so what would that look like for a reaction? Now we're keeping the methoxy butadiene in the same spot. So go ahead and push the electrons around there, same mechanism. But look, the position of the methoxy to the aldehyde is changed, okay? Now these are affecting not only the regio selectivity of the reaction now, and it's because we have unsymmetric, what? We have unsymmetric diene and dienophile, okay? Both of them have to be unsymmetric to worry about this rule, okay? Why? Because you see you have an aldehyde here and nothing here. And you have a methoxy here and nothing down here. So these two ends, there's no symmetry here, okay? You don't always need to worry about this rule again. In fact, I consider this a more advanced topic even than the endo thing. It's a little easier to see but oftentimes you got to do the endo rule and this Regio selectivity issue. So what's governing this? So we call this first, let's look at this. So if the group here and here end up 1,2 to each other, we call it the 1,2 type product. If we flip it over and have the opposite Regio selectivity, we have this group, what, 1 and 3 to each other. We can't get 1,4 with this. And first of all, what do we call this group here? It's got a lone pair here. We've already talked about how this group here is an electron withdrawing group. And we've talked about the resonance there already by making this carbon, what, partially positive. And we'll have to look at the, what, resonance structures of both of these to understand this. Well, what are we going to call this guy now on the butadiene? A donating group, right? And how is it donating? So, yeah, it is a donor group. This lone pair right here can donate in, okay, and make the diene more electron rich by resonance. Now, it's not always just an X group with a lone pair by resonance. It's also an alkyl group. If it's got a bigger alkyl group out there, that's also considered an inductive donor, okay? So it can be alkyl or nitrogen or oxygen, something with a lone pair that by resonance can donate in there. So which one do you think is going to be favored? 1, 2, or 1, 3? Yeah. 1, 2, okay. And why? We're going to have to look at the resonance structures, okay? And let's look at this one first here for the diene. And if we do that, we get this. You see a full charged species there. Everybody see that that's the resonance structure? I should draw a double-headed arrow for that. Okay. You see the lone pair came down, formed a double bond here, pushed the electrons over, and now we have an anion out on that. So there's our, partially negative charge here on the end of the donor. If the donor's at the 1 position, it makes the 2 and the 4 position more electron rich. You can see that. We could have stopped with the resonance structure right here with the negative charge there and the double bond here. Same thing, okay? It's making this end more electron rich. And we've already looked at the resonance structure of the dienophile. What will it look like there? Look like this. Okay. Now this is conjugated to a carbonyl, you see. So there we're pulling the electrons the other way to what? Put the negative charge up on oxygen. Now, we worry about sometimes, well, positive charge on oxygen. Well, that's from the lone pair, okay? Being able to resonance donate in there. That's okay, okay? It doesn't violate the octet rule or anything like that. Yeah, it's not beneficial to have a positive charge on an electronegative group. But temporarily, what this is doing is souping up the electron density at this position, okay? Due to that resonance overlap. And this, because the carbonyl is conjugated the other way, you see, this one's right on the carbon of the pi system. This one's conjugated to the carbonyl off the pi system. So there's a difference there, okay? Well, what do we have? We've got this plus charge here. And let's use this to do the Diels-Alder, okay? You can consider a stepwise approach. Now, that's not what the mechanism is. The mechanism is a concerted mechanism. But you can use this to rationalize this Regio selectivity. So let's just do that step right there. What are we going to get? OMe. We'll have our double bond there. And have our aldehyde there. So we just made this bond. Okay. And now you can see the rest of the Diels-Alder. We've already moved the pi bond over here, right? That's where it ends up in the Diels-Alder. And then move this down, move this over here. And then that goes directly to 1, 2. Okay? You can see how that works. Well, we ought to compare it to 1, 3. Let's see, can we do 1, 3 here? Well, if we have 1, 3, you see this is our partial negative end of it here. And this is our partial positive end right here. You can't really see it yet leading to 1, 3, but let's draw the resonance structures. That's what it would be right there, negative. And here would be what? Positive. And putting them together 1, 3 like this, let's see. We don't really have this here. Our plus charge is out here, you see. If we push that in there, we'd be pushing that, we'd have a negative charge next to a negative charge. Okay, so that's not going to work. We could go backwards here, put that electron density here, and that still would bring this back up here. The partial negative would be over here. You see, that's not part of the Diels-Alder reaction. So here, you see, we've got the positive end of this resonance structure with the negative end of that resonance structure. And that rationalizes the 1, 2 product being major. Okay. The 1, 3 process has the electronics mismatch. That's the partial positive end here. If we just stopped with that resonance structure and go back to our methyl ether there, we'd have a plus charge right there. That would be the resonance structure. And then plus with plus, that would be a problem. And then here, if we brought this back down, you see we'd have a negative charge right here. And so negative and negative would also be repulsive in that transition state. So the electronics, we say, are matched in the transition state with an unsymmetric diene and unsymmetric dienophile to give a 1, 2 type product. Okay. Now you can also get the 1, 4, but that's where you have a donor group at the 2 position. Let's look at methyl butadiene. And then we've got an ester or an aldehyde. I think I have the one for the ester here. Can we do the 1, 4? And yeah, so this would be the partial negative end. Due to resonance here, we could consider this resonance structure. Okay, because we have the tertiary position here. And this is an alkyl donor now, making this resonance structure the more important one. And then we have the more important resonance structure of the unsaturated ester here. Then we have negative with positive there. And then we can go back to this one here and push that over and put the double bond there. So what's our product? Well, the methyl group's at the 2 position now, not at the, oh, I got to move the double bond over to it. And then where's our ester? It'll be down here. And that's called the 1, 4 product, okay? That's because we moved the donor, this methyl group, over to this 2 position here. So you see the donor and the withdrawer either end up 1, 4 or 1, 2. And that's the example up here where the donor is at the 1 position. So those are the favored ones, 1, 4 and 1, 3 for the relative position of a withdrawer with a donor in that case. And here we don't need to worry about the endo rule, but let's see the example we just did up here with the methoxy one. We do. So let's do the endo rule for our methoxy example. There's our methyl ether. And notice our alkene geometry here is still E or trans. And then where do we put the aldehyde? Well, the aldehyde's going to be on this carbon tucked underneath. Okay. And that's endo to it. This hydrogen's right here relative to that hydrogen. So you can already tell, is the methyl ether and the aldehyde can end up cis or trans to each other in the product following the endo rule. Who says cis? Let's see. Nobody. Who says trans to each other? A couple. Are these hydrogens in the transition state cis or trans to each other? Who says they're cis to each other? Okay, yeah, quite a few kind of hesitate. Who says the two hydrogens are trans to each other? Okay, let's draw the product with the same geometry here. Again, this is the problem on the upper board right there, right? There's where our methyl ether will end up, right there. Okay, and where will this hydrogen coming off here, and the aldehyde will still be down right there. And if we pull that out and look at the flat perspective of that, we'll have the methoxy down, right? Because that hydrogen is up. And what? Yeah, that aldehyde is down. Okay. So they'll end up cis to each other by the endo rule. And they're 1,2 to each other by the Regio selectivity rule, looking at the resonance structure. That's a harder problem because it has those two aspects, Regio selectivity and endo selectivity. Questions on that? Could go through the models and see that. And there are examples of that on Chem352 also, where the Regio selectivity is an issue. All right, let's look at some other examples here. Let's look at alkynes. Let's look at alkynes as dienophiles. So if we have an alkyne conjugated to a withdrawing group, here's an alkynyl ester, triple bond there. And if we've got butadiene here, can do the Diels-Alder right here. We've got an alkyne here, right? sp hybridized. And so let's see, we'll still have the ester here, methyl ester. Well, what about here? We just use one pi bond of the alkyne for the dienophile, right? The other one is still there. So this forms cyclohexadiene products, okay? And do we need to worry about the endo rule or the Regio selectivity issue? No, not at all, okay? There's no stereocenters here. The molecule's flat, it's achiral, so you're off the hook there, but you can see it's got that position there. Let's see, could we react it with another equivalent of butadiene? Yeah. So now the issue, though, is this hydrogen and the ester are cis to each other, right? And so what's our product look like? It'll be a bicyclic thing. The two butadienes on the side, and then where do we need the ester and the hydrogen? Well, right here. We can either draw them both up or both down. So I think that's the product there. Does everyone agree with that? Is the ester and the hydrogen going to be cis to each other? Okay. And the two alkenes. Okay. How about this approach? What if we have a heterocycle? This is called furan. And let's react that with alkyne with two esters here. That actually makes it even more reactive dienophile because it's conjugated to two carbonyls. Let's just do the one Diels-Alder reaction. So right here, here, and push the thing over there. Now we got that oxygen there in the ring already. We've got to be careful of. And I always just draw the cyclohexene product first. Okay. Because that's what the Diels-Alder always forms. You should be able to always identify that cyclohexene product. And there it is. So where's the oxygen? It's going to be between these two. Okay. And let's see, we're only using one pi bond here, so the other's still there. And ester, I'm not going to draw out the esters again, but it's going to give that bridge bicyclic type structure there. And yeah, that would be the product, okay, using alkynes. All right, a different approach to working Diels-Alder problems is to be given a product, and then you're asked, what were the starting materials? What was the diene and the dienophile that you used to make a certain product? So let's see here. You're told there was a Diels-Alder reaction, and then there was a hydrogenation reaction, and you generated this product after hydrogenation. Oops. So can you fill in the Diels-Alder diene and dienophile, and can you fill in the intermediate for the Diels-Alder product? And then understanding where this went. Now, I'm kind of jumping ahead to a more complicated one, but we've seen these norbornene type products, right? And the norbornene usually gives an alkene over here, right? And they always involve cyclopentadiene as the Diels-Alder diene. You can see the bridging methylene right there. So you can kind of work backwards here. Hydrogenation means what? The alkene that was the Diels-Alder product went away. Remember, that's a reaction from chapter 9, I think, where we had different alkene reactions. We can hydrogenate or reduce those alkenes with hydrogen and palladium. So that alkene now is an alkane at that point. Now you should be able to see what the Diels-Alder cyclohexene product embedded down there. Okay, that sometimes is a hard thing to see. So it means we work backwards here, and we must have put on the dienophile here on the right. That was an alkene. And our diene must have been here on the other 4 carbons of the cyclohexene type product. So hopefully you can see that maps on back to something that should look familiar, right? Cyclopentadiene. There's our methylene sticking up right there. And there's the 4 carbons of the butadiene reactive partner. And then what's our Diels-Alder dienophile? Must have been this unsaturated ketone. Okay. So that's working backwards. And when you think about it backwards direction, that's called what? We have this open arrow here. Anybody remember the term planning a synthesis? Starts with an R. Retro, yeah, which means backwards. Retrosynthesis. And, we'll do more synthesis problems, and I'll show you the thought process here. But Diels-Alder is kind of limited. We can either, form the Diels-Alder alkene, and then we can do different things on that alkene. So I already showed you. There's a couple homework problems with osmium and maybe even the MCPBA, the epoxidation. So that's a possibility. But mapping it back to the Diels-Alder thing is kind of the trickier part here. Yeah, let's do another one here. This one's a little different. This one gives you a bicyclic product and asks you, how is this made using a Diels-Alder reaction? Well, analyze the position of the cyclohexene, right? Well, here it is. It's that bicyclic system. Now let's apply the retrosynthesis idea here. What diene and what dienophile gave rise to this product? and you can just push the electrons in the opposite direction. Okay, let's break this bond, push the alkene over, and break that bond. Okay. You could push them the other way, it doesn't matter, but we're breaking this bond here and this bond here at the allylic positions, right, on the Diels-Alder alkene product. And if we do that, what do we get? We'll get a butadiene up there. We're still connected over here, and we still have this ketone here. And we have what? The dienophile right there. Okay. So this is not a cyclic starting material, but what do we call this in the forward direction? We have the diene and the alkene of the dienophile linked together with a tether. Okay. All the examples we've seen before are bimolecular, two things coming together. Now they're within the same molecule. We have another term for that. Anybody remember if it happens within the same molecule? Intramolecular, very good. Intramolecular reaction. These can be favored as long as the ring that's formed on the side here. Notice we formed two rings in this case, this intramolecular one. This is a 6 ring here, and the Diels-Alder is a 6 ring. So that's actually especially favored because it's strain free and it's unimolecular kinetics actually because it's intramolecular in that case. And then there's other things we could do there, you know, with what goes on there. We do have these relative positions here. We do need to worry about the endo rule. I'll let you worry about that. These will actually end up cis to each other. Okay, and that's by the endo rule. When you do the transition state, you want the carbonyl here of the ketone tucked underneath the diene. That will push the hydrogen up, and this hydrogen here on the diene in that position is also up. And yeah, that'll be coming out. Yeah, won't worry about that. Let's do another retrosynthesis problem. How about this? We'll kind of keep this same pattern here. How about this one? Can we do a Diels-Alder reaction to form that? And let's see, we've got cyclohexadiene now. And we saw how we could form hexadiene with the Diels-Alder from an alkyne, right? Triple bond dienophile. And so let's break this bond here and go backwards and see what this maps onto, right? So do the retrosynthesis. What do we get? Diene up there. Now our tether looks like that. And we got a triple bond and then ester over here. And notice we're forming what? A 5-membered ring now here. So we can push the electrons around, do the Diels-Alder reaction in the forward direction. And yeah, that's strain free also. A 5-membered ring is okay. Okay. If you form a 4-membered ring over here, what's the problem there? Angle strain, right? That's not going to be favored intramolecular Diels-Alder, but these couple will be. And we don't need to worry about the endo rule. There's only one stereocenter. It'll form in a racemic fashion. So, yeah, question.
You need to spend energy to bend them into these shapes.
Yeah, the question is, do you need to expend energy to bend them into this shape or access the proper conformation for the Diels-Alder? Yes. So, you know, there's conformational freedom around all these bonds, right? But there will be a small population that will bump into the right Diels-Alder transformation. And because it's strain-free, 6,6 or 5,6, those will actually go. You do need to heat these up. I don't have the exact conditions, but both of these are high-yielding reactions. Okay, yeah. All right, let's see. Yeah, we could go over the homo-lumo basis for the Diels-Alder reaction, but I'd rather go to the overheads here and do the UV and also show you the synthetic examples of this. I could show you the homo-lumo explanation for the Diels-Alder. Yeah, let's see if we got time when we review later, maybe we'll look at that. But let's go to the overheads here and see what we need to do. I think I showed you this panel before. Oseltamivir, that's the generic name for Tamiflu, the trade name for the antiviral agent, developed to combat the bird flu a while ago. It's a form of influenza. The mechanism is it inhibits sialidase. And this is this big blue protein here. That's on the virus. That's needed to hydrolyze a polysaccharide on the surface of host cells, endothelial cells, in the air passages. That's where the infection usually starts there. This is designed completely using rational drug design. The 3D structure of the sialidase enzyme was known. The substrate for its substrate was known. So this drug was designed to fit into that active site pocket and be a tighter binder than the endogenous substrate. And that's a mouthful, but that's the basis of all drug design. Okay. You want to find a drug that binds more tightly to some receptor in the living cell that can inhibit that pathway, okay? Pathogenically, usually it's some rogue pathway that's out of control, and that holds for cancer as well as for infections from bacteria or viruses. You want to inhibit a pathway. And so this drug here, and then we see the Diels-Alder reaction right here, unsaturated trifluoromethyl acrylate ester. And it forms one stereocenter there. The diene is a simple one. We don't need to worry about the endo rule. How come we get one enantiomeric form here? 97% enantiomeric excess. Just the one stereocenter shown here. And that stereocenter dictates all the other stereocenters that are formed in the product. Obviously, more steps go on. But notice this is a chiral catalyst. We're not going over those aspects. That's an advanced topic for Chem 553. Take advanced OChem if you want to learn more about that. But conceptually, you can see why. This is Lewis acidic. It activates the carbonyl, lowers the energy needed for the Diels-Alder reaction. And that chiral catalyst is in proximity to these bonds as they form. And that controls the stereochemistry right there. Anyway, that's a modern example. The first examples, applications of the Diels-Alder reaction, done by R.B. Woodward in the 1950s. Remember, I told you the Diels-Alder was developed in the 1920s. It kind of languished in obscurity for a long time until Woodward showed you could use it to make these polycyclic systems. This actually becomes the D and the C ring of cortisone. And for the 1950s, that's a Herculean synthesis. It's about 20 more steps here to go here. He investigated quinones as Diels-Alder dienophiles. You notice the methoxy group's a donor on this side. And the two carbonyls over here are withdrawing groups on that side. So that's where it actually reacts over here. And the other thing to notice is this methyl and this hydrogen on the quinone are cis to each other. Okay. He can isomerize that with base over to the thermodynamically favored trans linkage there. But the initial Diels-Alder diene reaction gives the cis like we've been talking about there. But obviously many more steps, and yeah, don't worry about that. The other thing here with polyenes is that they absorb in the UV range. In fact, most unsaturated functional groups in organic chemistry absorb in the UV range. So this is traditional classical spectroscopy, where we shine light on a molecule and see where it absorbs, okay? And here's the full electromagnetic spectrum that you already know and love, from the high energy gamma rays down here to the low energy radio waves. And it's inversely related. What the frequency over here in hertz, and then down here the wavelength is larger there. It's because they're inversely related, right? Here's the basic energy equation. Planck's constant times frequency. Now remember what frequency is. Frequencies is events per second. What event are we talking about? As that photon comes past the detector, it's the number of peaks or troughs as it comes by per second the detector sees. The speed is the speed of light, right? These are photons or light particles, right? Speed and frequency are not the same. The detector sees a number of peaks or troughs per second, and that directly correlates to the energy, the frequency. And you can figure that it's the energy as those peaks or troughs bounce by. That's creating some energy, right? Okay. The speed, the propagation through the medium is the same. It's a constant, 3 times 10 to the 8 meters per second. Speed of light's a constant. But the wavelength is inversely proportional there. So frequency, or nu, is equal to the speed of light over lambda, the wavelength. What that means is longer lambda means what? lower energy. The longest wavelengths here are radio wavelengths, which can be a meter long. That's your FM radio and AM radio and the NMR spectrometer. All are in down this range. Here are organic molecules absorbing in the UV radiation, and that is electronic excitation, pi to pi star, okay? That's a different thing. We've already talked about IR. That's exciting what? Bond length vibrations and bond angle deformations, right? The wiggling and waggling in the IR range. That's a different thing than HOMO-LUMO electronic excitation that we've talked about. So we showed you the energy diagrams, you know, the number of molecular orbitals with the pi system. And here it is. You don't need to worry about these equations. We're not testing on the math at all. Just conceptually, the more resonance conjugation overlap you have, the longer the wavelength and the smaller the energy. Okay. So more conjugation means longer lambda. That's all you need to remember. And here's to get started here, isoprene or methyl butadiene. And here's the lambda max at 222 nanometers. That's a lambda value. We could convert that into a frequency value. It's in this range right here. And notice that's outside the visible range. So it's up here, you can't see it. And this is kind of blobby. These are coupled to a lot of other vibrations and motions in the molecule. So these tend to be very broad. But the peak, the top part here, is the maximum lambda for the absorption. And it corresponds to 222, yeah, and it's almost absorbing all of the energy at that point. And the rest is silent. This is going toward the visible range. Let's look at some other molecules here. So that's what we just looked at for butadiene. If you take the methyl off, it's 215. Don't worry about that. Ethylene, we need to really back up and look at ethylene, right? Just one pi bond. What's the electronic excitation? Well, a photon of light in the UV range will excite an electron from the HOMO up to the LUMO. That's all we mean, okay? It's not vibration, it's not rotation or anything like that. It's electronic excitation. And that's pretty high energy. That corresponds to 170 kcals per mole, okay? The UV is a higher energy process than IR. But if we have butadiene now, that's 4 molecular orbitals, right? So we have 2 filled here that are lower. And look, the gap between the HOMO and the LUMO gets smaller. So that means what? Lower frequency, lower energy, and higher wavelength. 215 versus 185 nanometer, okay? And then let's see, octatetraene, I guess we skipped triene. You can see the trend here, that's what, 8 atomic orbitals, so we need 8 molecular orbitals. And look, the HOMO-LUMO gap gets even shorter. And now we're in the visible range. Now we're absorbing this purple frequency, and we're seeing more of the red. So this molecule actually has a color to it. But that gap, you know, from this visible light, its lambda max is 400 nanometers now. That's about 90 kcals per mole gap here. Now we can keep extending that. We have molecules called polyacetylenes, where we have almost an infinite number of alkenes conjugated. And this HOMO-LUMO gap can get so small, it has a metallic luster to it. Okay, and that's because it's beginning to conduct electricity. And why? The filled to the empty gap is so close, these electrons can easily jump over. Okay, so there's the basis, right? The more conjugation you get, the lower the energy, and what, the longer the wavelength. All right, what else about UV radiation? Well, if it comes from the sun and hits your skin, it's good to have sun blocking agent there. And we have UVA region here. Don't worry about that. UVB. You've probably heard about that looking at your sunscreen or your lotion there. You want full coverage of A and B because they have both damaging effects on your skin. And then there's a lot of absorbing materials that have been developed to absorb that UV radiation instead of your skin. Some radiation can cause thymidine to dimerize. That can lead to skin cancer. And other things just cause, other wavelengths just cause inflammation in the skin, redness or a sunburn, right? And so if these agents are there, you see they're highly conjugated. And here's where they absorb. Okay, these are the lambda maxes here for the actual molecules. Synoxate is a cinnamate type thing. Oxobenzones, a benzophenone. highly conjugated, right? And then PABA, that's one of the original ones, para-aminobenzoic acid. That one has some toxic effects. That's been phased out. But you should have a mixture of UVA and UVB absorbers. But I just show that, and they have corresponding wavelengths associated with it. The bottom line, all you need to remember is what? The more conjugation you have, what? The longer or the shorter the wavelength? Longer. Okay, keep that straight. Because more conjugation lowers the gap and the energy goes down. But remember that frequency and that energy gap is inversely related to the wavelength of light, the distance between two. So review that, some of the basics, but don't worry about the math. Those are done. Very good. We'll see you Thursday. Watch the videos. See you next time. Okay, take care.